Hello everyone. This video is intended to show you how to use Julia in chemical engineering calculation. And for this video clip, the topic that we are going to focus in would be the use of steam table. Okay. In Julia, it is very convenient that we can load up the steam table library, which is called steam tables. So let me load up steam table and enter. While we are loading this library, let's switch to search engine to see the description or instruction for using this library. So if I search Julia and steam tables like so, the very first item here that you can find is basically the instruction how to use this library. And as you can see here, we can calculate pressure, temperature, volume, entropy, and many things, just like in what we are going to find in actual steam table. And you see the unit incorporating this library. If the steam is saturated, these are commands that you can use. And then for superheated steam and subcooled liquid, these are commands that you can use. So let me show you the problem that we can use as exercise for today. The problem is basically a mixer that we have superheated steam entering the tank. And it is called stream 1 here. Together, there'll be the liquid at stream 2 coming down. If you notice the temperature, 20 degrees Celsius and 50 bar, this liquid is supposed to be subcooled liquid. And then the stream going out, I'm going to call this one stream number 3, which is by specification to be saturated stream at pressure of 50 bar. So in order to solve this problem, if we want to know the required mass flow rate, M2, to satisfy this condition, in this problem, M2 is unknown at this point, and M3 is also an unknown. To solve the problem, basically we need two equations because we have two unknowns. The first equation that we can use would be the mass balance, which is input M1 plus M2 equal to M3, which is output. The second equation that we can use should be energy balance. In this case, since the tank is adiabatic, there's no heat, no external work. So it's basically input and output term would be the mass times the enthalpy. So the first stream, we have enthalpy of H1. The second stream should have enthalpy of H2. And then the output stream, M3, multiplied by enthalpy H3. Okay? So from the first equation, from this relationship, if I take M3 from mass balance to replace into energy balance, I can get M1H1 plus M2H2 equal to M1 plus M2 multiplied by enthalpy H3. So therefore, we will have M1 here and here, M2 together, so that we can put them together like this. M1, H1 subtracted by H3 plus M2, H2 subtracted by H3 equal to 0. Right? Then we can rearrange the equation to get M2 as we want. this is what we are going to use. Basically, we need the enthalpy of 3 streams so that we can calculate the proper mass flow rate of stream number 2 to satisfy our condition. Okay. Of course, since we have 2 unknowns, two equations, we can use solver as well, just like in video number 1. But just to make it simple for this video, I'm going to calculate it manually using this equation. So I'm going to highlight this equation. This is the equation that we are going to use. So let's start using Julia. The library is already called. We can enter the proper parameters for the stream, either line by line. For instance, I can say that P1 is 10 megapascal. I put pound sign here. Anything after the pound sign will be considered as a comment in the code, and everything highlighted in pink here will be neglected by the code. So this is a comment for ourselves. In this case, if you go back to the description of this function, you see that enthalpy, or the pressure that this library, the SteamTable library use, is in megapascal unit. So even though our system has pressure of 100 bar, we need to convert the pressure into megapascal so that the library will use the pressure accordingly. So 100 bar is 10 megapascal. Okay. So if you hit Control Enter, this P1 will be entered into program. Okay. So you can do it by make sure this is the real number and re-enter the number. This is okay as well. Or we can enter parameters in block. Okay. You can keep repeating entering the parameters line by line, cell by cell. But sometimes it is more convenient to enter everything in block. In order to do so, I'm going to delete this cell first and redo everything again. Okay. To enter code in block, basically we start with the keyword begin and hit 1 enter. The new line would appear so that you can enter your code. So P1 here is 10 megapascal. Again, anything in pink is considered as a comment, and Julia would neglect the code after the pound sign. T1 is 500 degrees Celsius plus 273.15 just to make it Kelvin. M1, that's 10 kilogram per second. This is for stream 1. If you satisfy with this block, then you can put N just to say that this is the end of the block. Then enter by using Control Enter to supply everything to Julia. However, you will see that the response from the computer would be only 1 line. The last line would be shown, even though these 2 lines is already accepted. Okay. I'm going to repeat entering the condition for other streams, stream 2 and stream 3 as well. So let's put it in block again. So if I put a comment for stream 2, hit enter, then I can enter pressure P2 equal to 5 megapascal. Temperature T2 of 20 degrees Celsius. Change into Kelvin. For stream 3, we have pressure P3 equal to 5 megapascal. Okay, and that's it. That's what we know. So we can put an N to the block and hit Control Enter to get a new cell. All right. So next, basically, we need enthalpy. In order to do energy balance, we need enthalpy H1, H2, and H3. I'm going to call the command from the SteamTable library. If you look at the command, for stream number 1, it is superheated steam. How do I know that it is superheated steam? I can check. If you go back here, I can get saturated temperature right here. If I provide pressure, let's say if I put pressure P1 using this command tsat, the computer would give me the saturated temperature back. So let's try that first. So if I assign tsat at pressure 1 to a variable named T1 sat, and I hit Control Enter, this is supposed to be the temperature, the saturated temperature at condition of pressure under 100 bar. Just if you want to show this one in Celsius, you just subtract it by 273.15 and we enter it again. That's 310 degrees Celsius. Our temperature T1 is 500 degrees Celsius as shown here. So definitely our stream number 1 is superheated. Okay. Since it is superheated, we need to supply 2 parameters, temperature and pressure, in order to calculate enthalpy. The way to do the calculation is specified here using this specific H command. And we need pressure and temperature as input parameters. So specific H of pressure P1, temperature T1, I'm going to assign this to a variable named H1. And keep in mind that the unit is in kilojoule per kilogram. I found some error in the website. The unit here is supposed to be kilojoule, not joule. So you can hit Control Enter to get H1 for stream number 1. For stream number 2, which is liquid, you can also check saturated temperature T2 sat equal to T sat of pressure P2 and subtracted by 273.15 just to get into Celsius. Execute the command. You see that under pressure of 50 bar, given pressure of 50 bar, the boiling point is 263 degrees Celsius. Our temperature is only 20 degrees Celsius. That means our water or our liquid at stream 2 is subcool water. So since it is subcool, we also need to provide 2 parameters. It is pure species single phase. So therefore degree of freedom is equal to 2. We need to specify 2 things, pressure and temperature. So it is exactly the same as in stream number 1. So enthalpy H2 should be specific H of pressure P2, temperature T2. Then I can execute the command. Okay. For stream number 3, which is saturated, if you go back to the code here, for saturated vapor, saturated steam, this is saturated vapor enthalpy. We will need this command, sathv. However, this command accepts temperature, not pressure, but we only know pressure. So therefore, we need to find temperature at given pressure first by using this command. Okay. So since we know pressure P3, we don't know temperature P3, we don't know temperature T3. We need to find temperature first using this command. Okay. So T3 sat is basically T sat of pressure P3. I can execute the command. Then I can find enthalpy H3 equal to sat HV, the enthalpy of vapor at saturated condition. Okay. Inside, it accept temperature. So the temperature is T3 sat. Then they can run the code here to get enthalpy. After they get all enthalpies, then they can just manually calculate M2 according to the equation that we just derived. Then after execution, you get mass flow rate here, 2.147. The unit should be in kilogram per second. Okay. So you can see that it is very, very convenient to get the information from SteamTable using Julia coding. And after you get the information, you can do calculation afterward easily, conveniently. Okay. So before we finish this clip, let me show you another thing. Let me emphasize on another thing. Normally, when we have SteamTable, the data in manual SteamTable does not contain subcooled liquid. Normally, we would make approximation. Okay. So if we make approximation that we use enthalpy of saturated liquid at 20 degrees Celsius instead of enthalpy of actual subcooled liquid. So let me make a comment here. In order to make comment, you can use the command MD, standing for markdown. Inside the quotation mark, you can type anything. For instance, if I type enthalpy of saturated liquid at 20 degrees Celsius. If I execute the command, this sentence would appear as a word. Then you can hide this command just to make your notebook a little bit neater to read. And it is rather nice to have some remark to yourself. Okay. So if I use enthalpy of saturated liquid at 20 degrees Celsius instead of using enthalpy of subcooled liquid, I can find enthalpy H2 saturated liquid at 20 degrees Celsius. Let me call this variable by its name, its lengthy name. Then this is liquid. So if I go back to this website, it's saturated liquid. We are looking for enthalpy. So therefore we need this command, sat.hl with temperature. The temperature is already found here, T2 sat. I found that already, okay? You can also use, we are going to use 20 degrees Celsius as temperature. So sat enthalpy of liquid at temperature T2. Run it, you get this number, and then you can recalculate the mass flow rate. I just copy this line, paste it here, and change the variable name. This enthalpy H2 will be changed to the one that we used for sat liquid and recalculated. You see that the enthalpy that the actual enthalpy, the correct one that we use subcooled liquid, the answer is 2.147. If we make approximation using enthalpy of saturated liquid at 20 degrees Celsius, the result is approximately the same. So that's why when we do the calculation manually, it is okay to use temperature of saturated liquid instead of enthalpy of saturated liquid instead of enthalpy of subcooled liquid, as long as we use the same temperature. Okay. However, if I use the enthalpy, let's say enthalpy of saturated liquid, but instead of fixing temperature, if I fix the pressure to 50 bar, Now I can calculate enthalpy H2 sat liquid 50 bar by using the same command sat.hl, because I'm going to find enthalpy of liquid phase at saturation. But temperature here, instead of using 20 degrees Celsius, I'm going to use temperature that corresponds to pressure P2, which is T2 sat. Okay. However, in this cell, I changed into degrees Celsius, but the steam table accepts temperature in Kelvin. So in this case, I'm going to drop this conversion to keep it in Kelvin and rerun this one. Okay. And then I'm going to put temperature T2 sat here and rerun it again. And then recalculate the mass flow rate. Changing here to 50 bar and use the corresponds enthalpy 50 bar. Rerun the code. You see that now the error is significant. Okay. So if you want to use enthalpy of saturated liquid in place of enthalpy of subcooled liquid, you need to fix the temperature to be the same, not pressure. Otherwise, the error will be tremendous. All right. So for this clip, this video, the purpose of this video is show you that we can use SteamTables.jl to retrieve the data from SteamTable conveniently. And there's so many data that you can pick, like gift-free energy, volume, internal energy, entropy, enthalpy, heat capacity, and so on. There's so many things. There's so many ways to specify the variables. You can put pressure and temperature. You can put pressure and enthalpy, and many, many ways. So it is rather convenient if you can look it up in this website, and hopefully you can use it conveniently, and hope you enjoy the video. Thank you.